And I think it's from the back.
Hi, everyone. Okay, so welcome to the AMI Grad Student Seminar Series. This is a new departmental initiative to reform the AMI Grad program. And this will allow students in their senior years to enhance their professional development skills. During these seminars, several grad students will give 3-minute elevator pitches on their research projects to different mechanical engineering alumni from industries, startups, and national labs. And they are going to assume an audience of non-experts in their fields. Each elevator pitch addresses 3 key questions in 3 minutes. The first one is a real-life problem the research addresses. The second one is a unique way to solve it. And the third one is its impact on society. Grad students and their advisors are invited to participate in this exciting event. And this week's research theme is Biosystems and Thermal Sciences. And we have really exciting talks coming up for today. So we have 2 guests and Michigan alumni with us today. And they will give their valuable feedbacks to our student speakers. And they are also serving as judges. So please welcome Rob Nidetz, who is working as LNF user Liason, and Greg Sommer, who is the CEO of Sandstone Diagnostics, Inc. So can you guys please introduce yourselves? Starting with Rob.
My name's Rob. I did my PhD in material science here at Michigan. After that, I worked at some small companies here in town, including neural implants as well as MEMS. After that, I was a postdoc in mechanical engineering. And before joining the LNF, I was a high school engineering teacher in Alabama. And we taught a course in engineering design and entrepreneurship. So, and now I'm at the LNF as a user liaison.
Thank you, Rob. Can you introduce yourself, Greg?
Sure. Hi, everyone. Greg Sommer. I got my PhD in ME from University of Michigan in 2008. My thesis was around microfluidics and clinical diagnostics, protein separation mechanisms. I then was a staff scientist at Sandia National Labs in Livermore, California for about 5 years. And then I started a startup company called Sandstone Diagnostics in 2012. We were actually acquired by LabCorp end of last year. So I'm now an employee, a technical director at LabCorp, working on integrating our Sandstone's technologies into laboratory medicine across the network of LabCorp labs. And great to be here. Thanks for the invitation.
Thanks for the time.
Thank you, Greg. We're really happy to have you guys here. And now I'm gonna read the rules and prizes. The first one is that each participant gets 3 minutes to present, followed by 2 minutes of questions and answers. So we're gonna have a timer, and this timer is gonna have a beep at 2 minutes. And with the second beep, you're gonna know that your presentation is over. Then the judges will record scores after every presentation before moving to the next presentation. Third, their presentations will be evaluated based on 1, the technical content, 2, the communication, and 3, the engagement. And in case the overall scores level, there's a tie, they will be resolved in the same order. So the higher score in technical content is the winner. 4, the participants will be awarded as follows: $100 to the first place, $50 to the second place, and $25 to the third winner. And also, all of the participants will be given a $15 honorarium. And 5, the decision of the judges will be final. With that, let's welcome Julio Ferreira from the Kaviany lab. Okay, so there you go.
This reminder that if you present in this area, we can actually capture a video. we just present.
You can full screen? No?
We have the time. Well, at 2 minutes. And the final one at 3 minutes.
Okay.
All right, good luck.
Is there a way you guys can share the screen with those of us via Zoom?
Sorry. Yeah, isn't the screen being shared? Oh, what did they say? I couldn't. Ask what they said.
From here we can share this.
Share screen, but I think it will be shared.
Yeah.
So,
you can ask
check if, what they said. Sorry about that. Do I have the mic? Hello? I think we got an instruction a while ago. Could someone repeat it?
Yeah, those of us on Zoom, we can't see the slide.
Oh, I see. Just a minute, please.
Thanks.
I think I shared.
It's already shared, right? Screen. Ask if they can see your presentation now. Okay.
It's already shared, right?
I mean, we are sharing a different view.
Oh,
Yes.
Hi. So for some reason, we have all agreed that boiling water and producing steam so it can propel the blades of a turbine, which in turn powers a generator, is a good way of producing electricity. In the latest report by the US Energy Information Administration, the energy matrix in the year 2021 was divided as follows. 61% came from fossil fuels, including natural gas, petroleum, and coal. 19% from nuclear fission, and the remaining 20% from other renewable sources, such as wind, hydro, and solar energy. In short, 80% of the electricity produced in the US consists of boiling some water, burning some fuel in order to boil some water, producing steam, propelling the blades of a turbine, which in turn powers a generator, and so on. Steam generation is at the core of the energy industry, and improving the efficiency of this process can greatly impact society. That's why in my doctoral research in the heat transfer physics lab, I focus on optimizing this process by employing metasurfaces that help promote a more predictable and efficient generation of vapor. Metasurfaces are sintered porous structure, uniquely engineered to facilitate evaporation by reducing the superheat required to trigger vapor formation. Less energy is required to generate vapor, leading to a more efficient phase change process overall. It all starts with a plane surface, and then different sized particles are combined to form porous wicks that help separate the liquid and vapor phases. Experimental results showed a 400% increase in the thermal conductance compared to the regular plane surface. 75% less superheat is required for the same heat flux, while simultaneously pushing the boundaries of energy density dissipation. Metasurfaces can be easily produced and readily implemented in most energy generating facilities, leading to reductions in fuel consumption. Speaking of fuel, the 4 times efficiency increase I mentioned a while ago can roughly translate to a 10% reduction in fuel consumption. And as we all know by now, and the Energy Information Administration corroborates, fossil fuels, mainly natural gas and coal, are responsible for virtually the entirety of electricity-related CO2 emissions, effectively meaning an efficiency increase corresponds to millions of tons less of CO2 and other harmful gases being released into the atmosphere every year, helping buying us some much more needed extra time to fight climate change. And according to the IPCC, we are going to need any piece of help we can get in order to keep global warming to less than 1.5 degrees in the coming decades. Thanks.
Last on time.
Yeah.
Pretty good.
Thanks. And for 2 minutes Q&A.
We have time for 2 minutes for questions and answers. So do you guys have questions? Or the judges can also ask, maybe?
Yeah, this is Greg. Hey, really nice presentation. He explained, I wasn't quite clear on the surfaces that you're modifying in the process. Is it the turbine surfaces? Can you clarify that?
Hi, the evaporator surfaces. So you're using porous wicks to reduce the required superheat, therefore generating vapor more efficiently in the evaporator.
I see, thank you.
Well,
so I think I have a question about the last figure here, or this graph. And so does it predict the future temperature rise in the climate, global climate? And you're trying to show that, or?
Right, so the last figure here is from one of the latest reports from the IPCC. And it's basically, you have 4 figures here. The big one is the rise in temperature in the coming decades with 4 different scenarios. And here is some small explanation of the scenarios, but basically we have to reduce the annual emissions, as in the figure B down here, in order to keep the global warming to 1.5 degrees. So we have a lot to do, not that much time. Even though we have to move from fossil fuels, we're still using them, so we have to do something about that in the meantime.
All right, thanks, Julio, for your nice presentation. Yeah, go ahead. Okay, let's go with Jamie Ferris from the Sienko Lab.
Before that, the scores from the list.
Oh, do the judges have the scores already?
Can just ask them to submit.
Oh, they need to submit them.
1 minute.
Okay, sorry about that.
Comfortable up here.
I think while we're waiting for them to figure out, probably it would be nice for us to let the speakers give themselves a introduction. We said that they're files, but
Sure, yeah, I can introduce myself. I'm a 3rd-year PhD student in the Sienko Lab, and I also work with Dr. Noel Perkins. So my research has consisted of looking at wearable technologies to help with balance rehabilitation, as well as athletic contexts. So I'll be talking a little bit about the athletics today. You can start, I think.
Do you want this?
No, that's all right.
Okay.
Thank you.
So at the end of 2 minutes, you'll hear a small thing. And then at the end of 3 minutes, you'll be all fine.
Running is one of the most popular sports globally, with over 60 million participants in the US alone, myself included. But we as researchers know a lot less about the mechanics of it than you would think. It's not that we haven't conducted thousands of studies, looking at what running mechanics help people to run faster. or what types of runs cause people to get injured. But at the end of the day, the vast majority of these studies aren't done on the trails or on the track where most runners are. They're done in the lab on a treadmill. And we hope that a lot of these findings are going to translate, and some of them do. But we've also noticed significant differences between these contexts. So why is it that we keep doing our research in the lab? Ultimately, it's where all of our amazing equipment is, right? So we have these incredible machines where we can measure the position of someone's foot or the location of their knee to within a millimeter. And that can tell us so much. But at the end of the day, these machines are very difficult to translate to outside the lab. So if we want to work in the real world, we need different tools. Recently, we've seen the rise of these new small wearable sensors called IMUs. And IMUs are wonderful for our research in running in particular. They're accessible, they're cheap, and they're everywhere. So you can wear them on your runs up a mountain or around a lake. Although, with most things, there's a downside, right? So these IMUs, they measure acceleration instead of position. What this means is that we need new novel algorithms that help us take this abstract acceleration information and translate it into features that runners and their coaches can understand and therefore use during their training. For example, if I was running and someone told me to lengthen my stride and that would make me less injury prone, I could, and I definitely would want to do it. If you told me, on the other hand, to decrease my accelerations at the peak of my stride, I'm not even sure what it would look like to do that. And this is what I study every day. So why is it that we look at the accelerations instead of these positions? It can be difficult to get to position. In my research, I'm studying a novel algorithm that does just that. It calculates joint angles during a run, and from that we can get information about stride length, how much someone's driving their knee, how they're contacting the ground, all those sorts of features that are physically meaningful and significant to researchers, as well as to runners and their coaches. In my preliminary research, I've applied this algorithm to walking, and luckily we've seen wonderful results. So we're really excited to get to apply it to running and see how accurate these estimations can be. Ultimately, our aim is to go out on the trails, join runners on their home turf, and be able to provide them with training recommendations using real-world data that will help them to decrease their injury rate and be more effective at their sport. Thank you.
Thank you, Jamie. Do you guys have any questions for Jamie?
I had a question. Really nice job. Can you give an example of some of the successes that you've had with walking? You mentioned you've been successful with walking and now we're applying it to running.
Sure. Yeah. So the system is that we have people wear IMUs on each body part in their lower body, and we're able to estimate their knee angles, ankle angles, and hip angles in 3 dimensions to within an accuracy that allows us to make meaningful estimations about their stride length and those sorts of features. Does that help?
Well, can you maybe talk about the impact, I guess, more clinically, or what does that mean for the runner who's trying to improve, or the walker?
Yeah, so ultimately what we're hoping is to be able to empower researchers to take the research that we've seen in the lab and test it out on the trails. So this would span research that's looking at, impact of stride, or the foot strike angle and amount of shock in the tibia, and therefore stress fractures and different injuries. And that's been researched in the lab, but we don't know how well it translates. Or on the speed side, we've researched how elite runners run, and we've tried to help people train to run like elite runners. But we only know how elite runners run on a treadmill. So there would be clinical applications from an injury perspective, as well as just performance-based applications for competitive runners.
Great, thank you.
Yeah. Any other questions?
So from a technical perspective, an IMU returns us like the angular velocity and maybe magnetic field. So how do you translate that to the joint velocities of the body joints?
That's a great question. Yeah, so I simplified by saying acceleration in this case. You're right that it includes a suite of sensors, right? So we have triaxial linear acceleration and triaxial angular velocity, as well as magnetometer readings. So what the algorithm does is it intelligently fuses those different readings together, estimating the error in each one, and therefore which one we should trust most in our estimation using an error state Kalman filter. Thank you. Yeah. All right, thank you so much.
Thank you, Janie. Have the judges submit their scores? Not yet? Let's wait a minute. And let's welcome our next speaker, Amin Reihani from the Reddy Lab.
Can you go full screen, please?
You got it? Okay. Just a second.
Maybe we can turn off this thing.
Yeah.
Okay. You'll hear the first beep at the end of 2 minutes and the final beep at the end of 3 minutes. Okay. You can start.
Hello, everyone. My name is Amin, and today I wanted to share with you our recent technique for quantitative thermal microscopy. As you may know, in the last 2 decades, nanotechnology has revolutionized many industrial sectors, including information technology and electronics, medicine, transportation, and energy. Key for continuous advances in nanotechnology has always been the ability to measure and quantify physical processes and quantities with nanometric resolution. Temperature is one of the most fundamental physical quantities, and it governs many chemical and physical processes. Therefore, the ability to measure temperature with nanometric resolution is crucial among various fields in nanotechnology. In this study, we have developed a novel technique for mapping the temperature with nanometric resolution. This technique is based on scanning thermal microscopy, where a scanning thermal probe shown by this orange body with a sharp tip and an integrated thermometer comes into contact with the sample and raster scans the sample as shown here in order to obtain the temperature field on the sample. However, the main problem with the scanning thermal microscopy approaches is that the tip sample thermal contact resistance, shown as RTS here, is an unknown quantity and varies dynamically during the scanning. And this prevents accurate and quantitative temperature measurements. To solve this problem, we designed and custom fabricated the scanning thermal probes with various integrated heaters and thermometers and very sharp tip. Using these heaters and thermometers and a dynamic thermal model, we are able to, in real time, measure the tip sample thermal contact resistance, or RTS. And this allows us to convert the temperature field that you will normally obtain using a scanning thermal microscopy, and it has many artifacts and is not quantitative, to a temperature field that is almost free of artifacts and is quantitative. The resolution of our technique is 7 nanometers, and the temperature sensing resolution is 50 millikelvin at a bandwidth of 1 hertz. The other advantage of our technique is that it's almost calibration free, and once you calibrate a single probe, there is no need for calibration afterwards, making it easier for researchers among various fields in nanotechnology to use this technique. With that, I wanted to end my presentation, and thank you for your attention.
Does anyone have any questions?
Yes,
I can.
This technique is kind of like atomic force microscopy.
It is a type of atomic force microscopy. It's essentially contact mode AFM.
Okay.
And you raster scan the sample and you can obtain temperature or thermal properties.
Okay. I was just curious if you're restricted between continuous or intermittent contact modes with AFM using this technique?
It's a contact mode AFM. Otherwise, the heat transfer would not be possible to detect the temperature.
Not even in the very short amount of time.
Yeah, the issue with very short time is that the thermal response of these probes is not very fast. So you have like a few tens of millisecond response time. So it needs to be in contact for a few tens of milliseconds for the probe to respond.
Gotcha.
Yeah.
Thank you.
Sure.
So what is the technique that you make this sharp tip?
It's a silicon oxide tip. So you essentially, you first deposit a low temperature oxide, and then you put a chromium cap on it. And this chromium cap essentially makes the position of the tip, and then you etch it. So it starts etching from the sides of the cap, and at the end, you will end up with this conical shaped tip. And at the very end, the chromium cap that you initially put there, it will essentially be detached and fly away, and you will end up with this sharp tip. So the radius of the tip in this case is 25 nanometers. So when you bring it in contact with the sample, the diameter of the contact patch with the sample is only 5 nanometers, and that determines our resolution, which is 7 nanometers.
Any other questions from the audience?
How much better is your resolution or your performance here, and what does that mean, you know, as you translate this into specific applications?
Okay, so the resolution we have is, in terms of spatial resolution, is I think probably one of the best in the literature. The specific advances that we have brought is that we have made this technique quantitative. We have made it to be in a way that if you measure 100 millikelvin temperature change, it is truly 100 millikelvin and not 70 millikelvin or 150 millikelvin. And we also have made it so that it is free of artifacts. So if you have a complex sample that has variations in topography and materials, as is the case of this sample. So here we have variations in topography and materials. This method automatically accounts for the artifacts generated by those variations and gives you a clean temperature field. In terms of the temperature resolution, 50 millikelvin at 1 hertz may not sound very good, but if you integrate this over long times, you can detect lower than 1 millikelvin temperature change on the surface. And we have used that, for instance, to measure cooling on electronic devices and so on. So lower than a millikelvin temperature changes can be detected if you just integrate your measurement for a long time.
Thank you.
Thanks. Let's thank our speaker, Amin, and have the judges submitted their reports yet? Yeah.
I'm ready.
Oh, you're waiting. But we can welcome our next speaker, Nadab Wubshet from the Liu Lab. You can introduce yourself while we wait for the judges.
Oh, okay. My name is Nadab Wubshet. I'm a fourth-year PhD student at the Liu Lab in the Mechanical Engineering Department.
We're good to go.
All right, so all good things start with cat video. And here we have a cat with a superpower allowing it to squeeze into a very small gap. And cells are equipped with a similar ability. Here we have, and they use it during cancer cell metastasization. So we have a primary tumor. And the primary tumor, a cell is going to dislodge and then squeeze into the epithelial layer to access the blood vessels and to form other secondary tumors all throughout the body. And cancer cell metastasization are responsible for 90% of cancer-related deaths. So how do cells do this? How do they change their morphology and mechanics? And the usual suspect is the actin cytoskeleton. So the actin cytoskeleton self-assembles to form these organized networks, complex networks all throughout the cell. Actin binding proteins are actually responsible for making different architectures of actin networks inside the cell. Some form dendritic networks, some form bundles, some form crosslinks. Cell biologists using traditional methods in studying cytoskeleton and actin mechanics inside a cell they use in-cell in vitro platform, which is all cell biologists use. For example, in this case, they study transition of actin networks from one network to another by controlling an actin binding protein. So as you can see, it goes from one network from another, going from the left to the right by controlling one actin binding protein. And that also manipulates the cell function as well. However, the problem with this method is that the cell is just way too complex. So this is a map showing the protein to protein interaction in C. elegans, which is a simple organism. And as you can see, it's very complex, meaning that controlling cellular process or trying to understand the cellular process in such a platform would be very difficult and minimizes your controllability. So what we do is, the good thing about is that cell biologists have discovered a lot of cellular components inside a cell. So we have a toolbox with a good understanding of what each component is, what we have available component that we have. So as engineers, we're going to use this toolbox and try to design something that looks like a cell or that mimics a cell. So here we have an actin network confined inside a vesicle. The vesicle is made up of lipid bilayers. The lipid bilayers is also what makes the cell membrane. The size is cell mimicking, so we have a confinement that mimics a cell as well. So using this method, we can measure, we can try to study morphological changes as a function of actin binding protein. We can try to understand cellular mechanics as a function of actin networks inside these confinements. Not only we can use this platform to study and better understand cancer cell metastasization, but we can also design this minimal cells towards a more complex and functionalized cell-like cell mimicking system that allows us to replace real cells. So for example, if you have a problem with blood clotting and you're injured, we can design this minimal cells in order to replace cells or in order to replace platelets to treat for medical treatment. Yeah, thank you.
Thank you, Nadab. Does the audience have any questions? No?
Okay, thank you for exciting talk here. So I think you're synthesizing this engineered cell in this case. And so in terms of functionality of your synthesized cells or vesicles, how close or how similar to the real cell structures and functions?
So when encapsulating actin, the structures that are going to form are consistent with what you would expect inside a cell. So for example, if you expect a certain type of structure by encapsulating a certain type of actin binding protein with the available actin filaments that you have available, then you would see a similar construction or architecture of actin as you would see inside the cells.
One more minute.
We still have time for questions if someone wants to ask. Okay, so we will wait until the judges have submitted their scores. And thank you, Nadab, for your exciting talk. Let's welcome Chris Argenti from the Shih Lab.
Hello, my name is Chris Argenti. I'm in the Shih Lab. I work on medical devices. So I will be talking to you about that today.
You can start.
Ready? Ischemic stroke occurs when there is an adverse coagulation of blood, which creates a clot. This clot then blocks a vessel within the brain. When this occurs, there's an inability to transfer oxygen and nutrients to cells, which can cause cell death. This is a major problem in the US with approximately 800,000 cases per year and 140,000 of those resulting in death. There are currently two solutions to this problem. First, thrombolytics, a systemic approach to try to dissolve the clot chemically. This is only 25% effective. Second, mechanical thrombectomy. there are two types of mechanical thrombectomy currently available. The first, stent retrievers, which are a wireframe structure to try to grab the clot out of the vessel. The second, aspiration catheters, which utilize vacuum to try to suck the clot out. The combination of these techniques is still only 48% effective. This is due to the high fiber nature of these clots, which make them tough to get out of that vasculature. Our solution, cutting-based mechanical thrombectomy, which utilizes aspiration catheters with an embedded cutting tool. Our device is brought to the clot where it engages the clot with vacuum. It fragments it with that cutting tool and evacuates it from the body. Our research focuses on twofold. First, clot analog fabrication. How can we test this device with it when it's not in a human body? And so we try to mimic those clots we see in patients and use them for our testing. Second, we focus on design, modeling, and testing of the device to ensure its safety and efficacy. This research allows us to have the foundation for better clot analogs for a variety of different diseases. It also allows us to more efficiently remove those clots. And most importantly, it allows us to increase that recanalization rate for better patient outcomes. Thank you.
Thank you, Chris, for your exciting talk. Does anyone in the audience have any questions?
I have a question. Do you expect your approach to be considered a higher risk treatment approach compared to the other, the existing solution?
Yes, so one of the things with that cutting tool is it is embedded within the catheter, so it doesn't actually engage with that vasculature wall. But how we essentially test that is through, ex vivo brain model studies as well as animal studies. And after that test's done, we can test and look at that vasculature to look for damage to see if this tool would be causing that.
Thank you.
Any other questions? Oh, there's another question.
Thank you for your talk. So when it cuts the part that needs to be removed, how does it get access to the next portion of the part? Does it selectively remove the residues?
Yeah, so that's why we use that vacuum suction from the aspiration catheter. So our tool is embedded within the catheter, and when the vacuum occurs, it essentially pulls it to that tool, as you can see kind of here in this middle picture. And then, it fragments it kind of like a machining process where it essentially creates clot chips, which are then evacuated using that vacuum.
I see, thank you.
Anyone else? I'm coming.
Thank you. So what is the current status in terms of this animal study? I believe you have done this stuff with maybe a phantom or some structure or prototype mimicking maybe human tissue or this blood vessels, I think.
So for testing in lab, we have a glass phantom, which I think answers that question. So it essentially mimics kind of what our patient vasculature will look like. It's not necessarily ideal because it is glass, which is why we need to do those animal studies and ex vivo brain studies. With regards to creating the clot analogs, our work mostly focuses on human blood in our lab. So we actually work with the hospital to get components, RBCs, platelets, and plasma. And we can combine those in different ratios to create different types of clots. So depending on, when we add essentially more plasma, we'll have a higher fibrin clot.
Okay, thanks, Chris, for your exciting talk. We will wait until the judges submit their scores. And until that, we will welcome our next speaker, who is Andrew Stephens from the Kurabayashi lab.
Oh, cool.
Okay, I think you can start.
I start or introduce myself?
Yeah, we can start.
I'll start. Okay. All right. So there's currently a paradigm shift happening in medicine away from one-size-fits-all treatments towards targeted, personalized approaches based on a patient's individual biomolecular profile. And this is especially the case for immunomodulatory drug therapies, which target very specific components of the immune system. And the challenge here, and these therapies have been showing that they can very accurately treat very difficult diseases. However, the challenge is timely measurement of the blood biomarkers that they are impacting. Indeed, our lab is working to close this feedback loop between the drugs and the effect they're having on the body through the development of microfluidic biosensing technologies, such as this chip that we've made, which is a microfluidic chip capable of counting individual protein molecules in the blood associated with immune activation. And this type of approach, this timely monitoring, is especially important in rapidly evolving diseases such as COVID-19. And indeed, during the COVID-19 pandemic, my lab worked during the early months to process samples through our chip to hopefully illuminate some biomolecular understanding of what this mysterious and deadly virus was doing. And through collaboration with Michigan Medicine, every day we processed patient samples coming from the University Hospital ICU and fed the data back to the doctors in just a matter of hours. And with this data, the doctors were able to build these plots of the idea of how the disease was progressing in their body over time, and also to identify a cohort of some patients for an experimental compassionate use immunotherapy that ended up saving 4 patients that otherwise would have succumbed to a deadly cytokine storm. Now, the reason that, so our chip is quite fast, and then we can get these results in just a matter of hours. However, this endeavor required round-the-clock work by me and my team of lab mates to fabricate these chips, assemble the chips, and get them ready for measurement. And indeed, this is a problem generally in microfluidics, that a lot of these technologies are based on rapid prototyping methods that are great for small-scale academic endeavors, but pose significant challenges when you want to scale them outside of the lab. So therefore, my research is focused on developing scalable manufacturing technologies for microfluidics. For example, I've developed a method of fabricating that chip that we used in our COVID work using photolithography, which is a technique used by the semiconductor industry to print integrated circuits on a massive scale. And with this new technique, we're able to batch fabricate and pre-make our chips so we can spend less time pipetting and more time running samples and asking interesting questions in science and medicine. My name is Andrew Stephens, and after I graduate, I plan to commercialize this technology so it can be used by more researchers to hopefully improve more patient outcomes like the patients that we saved during COVID-19. Thank you.
Thanks, Andrew, for a wonderful talk. Do you guys have any questions, or anyone on Zoom?
I have a question. What's the biggest advantage of your technology over existing diagnostics for cytokines?
The biggest advantage is the sensitivity and the small sample size consumption. So using microfluidics, I didn't really get into this in the presentation, but using microfluidics, we can leverage, for example, microfabrication and the physics of scaling to run a lot of tests essentially on blood samples using very small volume and very quickly, and a number of other techniques to overcome like thermodynamic limits of reaction kinetics and so forth.
So is it speed? Is it multiplexing?
It's speed, multiplexing, and small sample size, sort of all of those benefits combined.
Thank you.
Hi, I'm curious, is this technology something you envision being applied in labs and places that already process this type of data? Or do you think that this is something that could be moved into hospitals and sort of decentralized, or even towards areas that don't currently have access to care?
Both. So in the short term, we're thinking just disseminating it to different researchers, this chip specifically, and eventually after FDA approvals and so forth, integration into a clinical lab.
Any other questions? Okay, there's another question.
Thanks for your talk. So in terms of scalability, the question I had is that the array of antibodies you show, how can you, like, I guess I'm trying to understand how can you, for example, process multiple samples? Because, okay, this is coding multiple antibodies, but how can you sort of introduce multiple samples to have some sort of like parallel processing?
Oh yeah, so this might not be clear. So basically one of these arrays is, if you can see those little spots on those chip, that's one biosensor surface. So each one of these arrays is, you know, maybe there's hundreds or so on a chip, and in each flow cell, there's hundreds of the sample arrays, yeah.
Okay, let's thank Andrew again, and let's welcome our next speaker, Safa Jabri from the Sienko lab. She's on Zoom, unfortunately. And then we will wait until the judges submit their scores. Are you ready, Safa?
Yeah. Can you make it full screen, please?
Yes.
Thanks. Can everyone hear me appropriately?
Yes.
Okay, awesome.
And we're ready for your talk.
Okay, great.
You're ready.
I'll start. For many of us, maintaining balance is an acquired skill that we rarely consciously think about as we navigate the world around us. In the background, however, our nervous systems are working hard at integrating sensory inputs and initiating corrective motor actions to keep us ready. As we age, maintaining our balance becomes harder. The sensory motor systems that allow us to walk and stand confidently decline over time, and we see many more older adults starting to walk cautiously and avoiding certain activities to prevent falls and injury. This can lead to an increasingly sedentary lifestyle. Balance and gait disorders, however, are not an inevitable aspect of aging. Research shows that balance training interventions guided by physical therapists can help patients maintain and enhance their functional abilities over time. In these interventions, physical therapists will assign patients exercises that challenge their balance appropriately. Then they will observe and evaluate their performance based on their expertise. Accessing such interventions, however, can be challenging due to practical considerations, such as the number of sessions insurance companies will cover, the patient load for clinicians, and the time and effort taken to travel to clinics to access training. In my graduate research, I work in a team of engineers and physical therapists to address this problem by creating tools that can automatically evaluate balance performance in rehabilitation without the need for a physical therapist in the room. To achieve this, we use small wearable sensors called inertial measurement units, or IMUs, that can measure movement. These sensors are used in my research to characterize the movement of a patient when they're performing balance exercises. We then use machine learning tools or methods to translate the complex sensor data into simple ratings of balance or performance assessments. This way, we can tell how well a patient is doing in a given exercise and measure their improvement over time as they practice at home. Early results from this research is showing us that the models we've built are able to match physical therapists' expert assessments of balance better than patient self-ratings would. As I continue to work on this project, I'm expanding this work to include a wider variety of exercises, and I'm collecting qualitative data to understand how physical therapists choose exercises for their patients to train. This information will be incorporated in our modeling approach to adapt and personalize training to patients' ability, thus allowing them to continue to train at home at the right level of challenge for them. This work aims to support older adults in our community to maintain their physical ability and independence by providing them with more accessible and data-driven balance training options. That's all for me. Thank you so much for listening.
Thank you for your wonderful talk, Safa. Do you guys have questions in the audience or over Zoom?
So is your research primarily focused on the algorithms or the hardware or both? Can you expand on that?
Yeah, so through this research, we are trying to correlate the wearable sensor data. As Jamie mentioned in her talk, it's pretty complex and abstract. We're trying to correlate them to physical therapist ratings. So we are at the same time collecting a wide data set of people performing exercises at different levels of difficulty. And then we're also collecting data from physical therapists to get a sense of how they would assess them. Then we're trying to create machine learning models that can correlate these two to be able to automatically predict how a physical therapist would rate someone just based on the sensor data.
Right, so you're using existing or off-the-shelf IMUs?
Yes.
Yeah, got it, thank you.
Any other questions for our speaker? All right, if not, let's give another round of applause to all our speakers. And now we will wait until the judges submit their scores, and then we're gonna have general feedback by the judges.
So Greg, Rob, if you can provide some feedback or comments or share your experience in presenting your commercial products to potential investors, that would be really great.
Sure. Rob, do you want to go first?
Sure. One of the things I thought that everyone did really well was communicate what you guys were working on. It seemed like all of you cared about what you're working on, so that's important. Because if you get up there and you're just kind of droning and you're not passionate about it, then anyone who's looking at you said, this person doesn't care. So if it was for entrepreneurship, I'm not going to invest in you if you don't care about what you're doing. And if it's an interview, if you don't care about your work, then maybe I don't want you working on my team. So the fact that you guys all were passionate about what you do is very important. Sometimes less is more. I felt like the most effective presentations had kind of the cleanest slides. Those that were a little bit busier tended to lean more on the figures, and we were paying more attention to what was on the slide than what you're actually saying. So really sometimes focus on getting to the root of what's most important before you kind of put it on your slide. Yeah, Greg?
Yeah, sure. I think I would echo those sentiments. Kudos to you all. I think very well done. I think being able to concisely and clearly present your research is a difficult skill, and it's a learned skill, and it takes a lot of practice. So, stepping up to participate in events like this, I think it's really neat and important. Definitely, yeah, I want to see more of that. I wrote down a few, I guess, things learning from pitching to primarily investors over the last decade or so. Some general principles with pitching that it's really important to connect immediately with your audience. That first sentence or two are crucial to really engage them. And as a general principle, especially when you have a short talk or pitch, you want to start big and you only want to crescendo from there. And you really want to leave them with, wanting more. Your goal is not to get a yes or no in 3 minutes. Your goal is to get to that next meeting and focus on, give them enough to, give your audience enough to, want to come back, ask some questions, set up another meeting to take it to the next step. That's really all you're trying to accomplish. It's important to know your audience. Obviously, I think you all did that very well today. If you're going to speak differently if you're talking to a room of engineering PhDs versus venture capitalists or people that don't know anything. And it's it's okay to really dumb it down for that audience if that's appropriate. And actually, it's a good skill to be able to learn how to communicate what you do on various levels. With pitching, it's always good to have a really clear ask. You know, that's a little different from today. You're not out there raising money, but if you are raising money, it's important to be very clear about what you're asking for with very defined and reasonable milestones around it. And then the last point is just, it's all about repetition and at bats. So, you know, the first time you start pitching, you're gonna be bad at it like anything. And the more you do it, it's important to do it a lot and then iterate every single time. And actually, one of the things that I found was most helpful is or effective, I guess, in helping improve is to have a friendly person in the audience in the room, someone who can watch the audience, see, you know, when are they sitting up in their chairs or asking questions, what catches their attention, immediately debrief as a team after you pitch to think about, okay, what worked, what didn't, how can we make it better? Write those things down, literally take notes after everything you pitch, and then make improvements, and you're only going to get better with those repetitions. But really nice job with all of you, and it's exciting to see all the really impressive projects that you're working on.
Okay, great. Thank you, Rob and Greg, and really appreciate your participation here. And so I'm gonna make a closing remark and also make an announcement for the winners of this competition. First of all, I really thank all of you guys who are participating in this event and then responding to my invitation. So it has been really great, and we really enjoyed your presentation in this case. So most important thing is that I want you guys to enjoy this stuff. I mean, maybe this kind of competition format may make you a little bit nervous about this situation, but I would like you guys to really enjoy this event, and then also getting a lot of good lessons from our outstanding alumni here. All right, so then I'd like to make an announcement. First of all, third winner, Andrew Stevens. Okay, Andrew, please come here. Just come here. Sorry, I don't have any token, but you're gonna get this some paycheck or whatever. And well, good job. All right. So okay. So take a picture. All right. Well, congratulations. Yes, you can just go ahead. You can sit. Second prize, or second winner here, Safa Jabri. Safa, okay, you did a great job. Well, congratulations. I cannot shake your hands here, but virtually I'm shaking. All right, very good. Wow, good job. All right, then the first prize winner is Chris. All right, Chris Argenti. Please come here, come over here. Well, very good job. All right, and look forward to your device to work anyway. Okay, thank you, Chris. All right, good job. And then those who didn't get this surprise, and then don't worry, you get the $15 honorarium. So anyway, I mean, yeah, don't be sorry if you didn't get the prize this time, but since you have this kind of experience and learning really good lessons, next time you're gonna be a winner. So let's thank all of them, and then let's say thank you. Okay, well, thank you guys, and thank you, yeah, MEGC folks.
Thank you, everyone. The food, we have a lot of food there at the end, so please feel free to grab whatever you'd like.